Hi, my name is Ivan Novick. I'm from the United States and I work for Pivotal, and I've been working on Postgres technology for the last 8 years and specializing in data warehousing based on the open source Greenplum database. And I'll be talking today about the open source Greenplum and how it can scale Postgres out to really large instantiations, and you can process lots of data in Postgres database with this technology. So looking forward to it.
Hello, everybody. Thank you for attending the talk today. I will talk about the analytics use cases and how we can take the Postgres database kernel and build a scale-out data analytics processing for large data sets. This is around the Greenplum Database, which is a product that we've been working on now for over 10 years. So let's start out and talk about what is Greenplum and how do you make Greenplum? First of all, you start with Postgres. Then you're going to need a lot of Postgreses. These Postgreses themselves are slightly modified to enable the ability to communicate together and to act as one database. And then we need to account for high availability in this cluster. So at a high level, that's what is required to create a Greenplum database. Now, before I get started, how many people here have heard of Greenplum before? Okay. One of the questions we frequently get, because for a long time we've been building Greenplum on very old versions of Postgres, and we get a frequent question about what version of Postgres we use. So currently we do use Postgres 9.1. And we're in the process of changing that to pretty much the current versions. And you'll see that coming in the next short time period, that it will be based on the same Postgres versions that you're familiar with. So that shouldn't be a concern for anybody. Now, why would you want to do this anyway? Why would you want to combine lots of Postgreses and create one big Postgres? What's the benefit? Well, you can do a lot of the same things you can do with Postgres itself, right? You can ask questions about your data. You can combine relational data through user-defined functions, and through extensions you can add rich data such as geospatial data, etc. But sometimes, what do you do if you have lots of data? What if you have tens of terabytes or hundreds of terabytes or petabytes of data? How can you store that and query that in Postgres? For example, let's say you work at an internet company and you want to store all of the traffic from the activity, such as what advertisements you showed or what pages were viewed. That can quickly grow into hundreds of terabytes or petabytes of data. And how are you going to store that in Postgres? Or let's say that you want to do some large-scale anomaly detection. So for example, if you work for, let's say, a government agency and you want to do detection of fraudulent activity, and you need to have a very large system. Another case would be you have very complex questions you want to ask. So in the case of actually the Japanese government, they're using this database, this technology, in order to do forecasts and predictions around traffic and weather. So it's really about the problems when the data size starts to grow and you need that capability. So how does this really work? How is it implemented? First of all, the key concept in this is a massively parallel processing version of Postgres. So in order to create a, as we say, MPP version of Postgres, what it means is that any one query, single query, needs to be handled in multiple servers. So if you ask a question, for example, count the sum of rows where the cookie ID from the web traffic equals XYZ. Well, we want to be able to do that one query, but have hundreds of computers contribute to get the result 100 times faster than if you did it in a single computer. And in order to enable that, we need to tap into the database workflow at the time of query optimization or planning. So when a query comes in, we need to be able to take that and create a distributed query plan, which can then be sent to many Postgreses in one. So one query can be handled by lots of systems, lots of Postgres instances. That's different than your classical sharding, where, for example, you say, well, let's just divide the data based on some algorithm and say, these customers will be in this Postgres, those customers will be in this Postgres, and then you could route your queries to the right one. In that case, you're still just doing each query on one Postgres, whereas what we need to do for analytics is to do a single query across many Postgreses and have them all contribute to that work. So this is how it looks like. The query comes in through the normal port, Postgres port, and the parser will accept the connection. The parser will break it down into Postgres understandable logic. And then from there, the query optimizer will go and create the plan, which is a distributed query execution plan, with the knowledge of the database statistics and the knowledge of how many Postgreses are part of this system. And then it will introduce a new component, which is not in traditional Postgres, which is dispatch. So the query will then be dispatched to all the Postgreses so that they could all execute their part of the plan. From there, one more key differential between a single host Postgres and a MPP Postgres is the ACID and the transaction management. So if you're going to be doing a select, that's straightforward. But what if you're going to be doing a multi-statement transaction? A multi-statement transaction needs to have a way to maintain the ACID properties of Postgres, but at the same time operating across a cluster of databases. So for that, we have a distributed transaction management where there's not only the transaction ID, but the distributed transaction ID, and together these things will enable for maintaining the traditional semantics you get with Postgres ACID, but at a larger scale. Another key component here is when users want to deploy this out into production systems, they have an expectation around high availability. So given that we're already running tens or hundreds of Postgreses, we want to also handle the event of a single host failure, and that you can have multiple Postgreses that can redundantly store and process the same data and create for a highly available system. So what we do is we basically have pairs. Every part of the system is divided into pairs, and there'll be two Postgreses running on different hosts for every role. And what that means is that if any host goes down, you still have the ability to automatically fail over and keep the entire system up and running. Now, when you go and create a table in a MPP Postgres, the question is, how can you, try this one, how can you ensure that the data is divided evenly between the systems? We'll see. So you create a table, and you want, this is for example an orders table, and we want to ensure that this table can divide the data across hundreds of Postgreses. So the traditional, and this is not, Greenplum is not the only MPP database in the world. There's quite a few, not all based on Postgres, but this concept here of how this works is that when you create the table, you basically take one of the columns, identify that column as the column which will force the distribution of the data. So in this case, we have an order table, and we divide the data based on the orders. So we can take a hash of that column, and based on just the algorithm, the hash algorithm, we can say, okay, if that is order ID 43, we hash it, so that belongs in this Postgres over here. So we evenly divide the data between all the Postgres databases equally by selecting one of the columns in the table and have the database automatically push this data out to each Postgres instance. This provides so that when you query the data, for example, you're going to say select count star where, each one of these Postgreses on the right side of the picture can work independently, and that can be propagated up to some sort of an aggregate operator that can sum those up. So this count can be done in a massively parallel fashion, or any type of query. Recent versions of Postgres have introduced partitioning, and for large data sets, partitioning is very important, because with partitioning, you can physically separate the data based on some characteristic, for example, time, and this will allow you to dramatically reduce the amount of data you're going to process for any given analytical query by looking at the where clause. So for example, here is a table of a sales database, and it's divided based on time. So you can imagine you have 100 units of time, let's say days or weeks or months. And if people are doing queries that are referencing where day equals something, then we know only one of those partitions is important, and the planner or the optimizer can eliminate and only process that part of the data. So for example, if you partition your table 100 times, divide the data into 100 partitions, and that could enable you to do aggregation and analytical queries 100 times faster than if you had to process the entire table. Now, once you start dealing with really large data sets, one of the things people are going to care about a lot is storage space. And so we've introduced a couple of different, call them pluggable storage models, which can optionally be used to condense the data. So if you're, again, dealing with a petabyte of data and you don't run any sort of compression, it's a huge wasted opportunity. It's going to, with good compression, you can chop it down by 90%, your data storage. So when you go and create a table or a partition in this version of Postgres, you can choose to make it a columnar store or a compressed store or an external store, and this can allow you to really make a petabyte database only take 100 terabytes of space or something like that. Now, when you combine these tactics and techniques and say, okay, we're going to distribute this table based on the order ID, but we're also going to partition it based on the date. So for example, let's say we had 12 Postgreses here in this picture, and let's say that we had 100 dates. So what that means is that, first of all, you've got 12 different computers that can answer a question instead of just one. And if the question is only about one day, then each Postgres only has to process 1% of the data. So you're essentially getting 1,200 time performance gain by distributing it to 12 systems and then partitioning it 100 ways on each one. So something that takes, let's say, 1,200 minutes to process on Postgres could take 1 minute to process in this format. Right? So 1 minute versus 1,200, it's worth getting it set up right to get that kind of result. You can also use indexes. Now, indexes won't help you when it comes to analytics, but if you're storing, for example, shipments and you wanted to have the ability to just do a lookup, what we can do is we can do indexes at the Postgres database level. So you can have, again, your 12 Postgreses, each one could have an index on the same table, and you could rapidly search for items you're looking for. Some of the other innovations that the Greenplum team has introduced help with large communities of people who want to ask questions about the same data. So once you have a petabyte of data, you really don't want to start making lots of copies of it in order to support more users. You're going to want to have one copy of that petabyte of data, and then have a way to allow lots of people to query it at the same time. And so in order to do that, we found that we needed a more robust way to control how much resources each user is using. Because people who, let's say you open up to a 20,000 person company, this database, and one of those people writes a query that tries to multiply infinity times infinity, they're going to take the entire database down, right? So what we do is we introduce at the Linux kernel layer grouping so that the users get routed into a group, and that at the operating system level we can guarantee each user group to only a certain percentage of the resources and prevent one user from dominating the system. An additional problem we faced when taking this to large-scale customers like banks was that they wanted to analyze the data with Python and R, using PL Python and PLR. And there's a lot of interesting libraries in PL Python and PLR through the open source libraries. But the fact that Python and R are technically untrusted was unacceptable to the banking community and some other large companies. An untrusted programming language means that you have to be the database super user to install functions, and that once you install that function, you basically have access to the file system and to the database server and can write any arbitrary code. So we introduced the container technology that can help with that problem. For the analytics themselves, there's another open source library called Apache Madlib. It's part of the Apache Foundation, but it's designed to work with Postgres and distributed Postgres systems. And this library comes with a full suite of machine learning algorithms. So for example, if you have people in your peers that want to do machine learning and they think, oh, I need to get a copy of all the data and use, let's say, Spark or something to do machine learning, well, if they just installed Apache Madlib, they can do it directly in Postgres. And so we've built this library over about a 10-year period, and it comes with all the same algorithms that you get in modern machine learning platforms, but they run in the database. So you've got an in-database machine learning tool set you can use. It also includes graph analytics, so you can ask questions like, what is the most popular point in a petabyte scale graph? The standard libraries from Postgres will work as well, but at a larger scale. So let's say you had a geospatial data, and you were doing a lot of work with geospatial, but you found, now I want to store the history, right? So, for example, in the United States, we have a company called Uber. I think, well, in any case, the point is that they've got all the different taxis. And what if you wanted to create a database where you store, where is every taxi? And where were they every 5 minutes for the last 5 years? And where were all the people who had the app? And where were they for every 5 minutes for the last 5 years? Well, it's going to quickly become billions of geolocation points, and we need a way to scale that out. Not that that's a real customer if you're watching this on video. But in any case, the point is the same, is that you want to store a huge number of geospatial objects and leverage all the technology built in Postgres over the last 20 years to do geospatial analytics. Well, it can be done at scale by doing MPP. Okay, so as far as where we want to go with this technology with Greenplum, we're really strong on analytics, but we think that over time there'll be a convergence where people want to have the same database running for both analytics and transactional workloads. So over time, we want to take this technology to be able to be really a technology that can scale Postgres out and to leverage infrastructures like some of the other talks you're seeing today about Kubernetes. I think Kubernetes is really a way that can create elastic environments. And once you have elastic infrastructure, now we need a way to make the database elastic too, and to scale out from one Postgres to 10 to 50 to 100 back to 50, and to make it a holistic system that can handle your analytics and your transactions. And so that's what we're working towards over the long run. And pretty confident that with a technology stack like that, that we can achieve in Postgres what Linux achieved in the operating system world, which is to really get away from the idea that one large company would build a proprietary operating system, like let's say IBM AIX, and then it becomes so popular. By everybody contributing to Linux, it became popular. And I think by contributing to the scale-out capability of Postgres, that Postgres can really become that future for databases. Now that being said, when we look at the analytical requirements of end users, the database is just one piece of it. And so I wanted to share with you some thoughts on what would a full stack look like for analytics down the road. So leveraging elastic platform like Kubernetes and having the ability to scale and to create additional instances and containers to run your workloads, then we need a few other pieces. So we're going to need the Greenplum piece to do, or the MPP Postgres piece in order to do your SQL workloads. But what we find talking to customers is there's also other kinds of analytics which are not database workloads and they're not SQL. And for that, both TensorFlow and Apache Spark are popular, and they could be part of a full stack platform for analytics. And then really seeing a lot of value in Kafka as well. So Kafka has the ability to do high-speed data ingestion. So if you wanted to have real-time processing, you could have millions of events being processed every second, captured into Kafka. The Kafka data could be loaded into Postgres for querying in real time, and it could also be accessible to non-SQL and non-database analytics. And then all of these different analytics then could be pushed out to an in-memory cache layer if you want to sort this out to a web application or a mobile application. So as far as the competition in the big SQL area, there's a lot of proprietary products like Teradata and Oracle, and then in non-scale out, in single node, we've got Postgres and MySQL. So we want to see if Greenplum can then be that open source technology that can scale. How about case studies? Okay, so some of the people who've been using Greenplum and getting good value, there's a lot of banking companies who use Greenplum around the world, probably close to 100 banking firms. And they can take their millions and billions of calculations that they need to create to understand the risks. So when interest rates change, when all the different factors in the economy change, they need to calculate the potential risks. And that comes out to millions and billions of calculations that they want to store in a database and query in multiple ways. And so we have quite a number of large customers using Greenplum for this type of application. Another interesting one is for anomaly detection. Anomaly detection in general is very suitable for big data analysis, and in particular for security, corporate security. When people log into a secure site through a key card, when people log into secure computers, when they access any kind of system access that produces an event record. And for a large company with hundreds of thousands of people, how can you have any sense of any either on-purpose bad activity or non-on-purpose? For example, if somebody's computer was hacked, their computer could be being used without their knowledge. So all of their system access can produce a pattern of activity, and we can help to detect irregular patterns of activity through queries, and then to create reports of potential issues. Predictive maintenance is another very kind of formulaic problem that we see a lot of people trying to solve. So for example, let's say you have oil rigs or expensive manufacturing equipment, and how do you determine when to take it out of service and start fixing it? Well, you've got all this sensor data, and the sensor data can be indicative of when it's going to fail. It's difficult to know that manually, but by storing all of the sensor data, the Internet of Things data in a database, and then running predictive models on it, we can detect and predict that, okay, this system needs maintenance, or else it's going to fail in the future. And what we want to do is we want to be on that curve. We want to take a system out for maintenance before it becomes failed, but not just proactively all the time and just wasting money and interrupting service. Some other use cases, without going into much detail, that are quite popular would be forecasting demand. So if you're producing something like semiconductors or even clothing, how do you know how much to produce? This can be predicted based on data modeling. I'll just talk about the churn reduction, which is, let's say you're a telephone operator, and as a telephone operator, you want to identify signals that a customer is ready to leave your telephone company and go to another one, based on their calling pattern, based on their billing pattern, based on all these things. Once you identify unhappy customers, you can take action. So these are real-world problems that can be solved with a powerful Postgres database, but it needs Postgres all working together, right? Hundreds of Postgreses together to solve this problem. It can't be done by one. Okay, so how can I get involved? If you're interested in Greenplum, how can you get involved? Well, luckily Greenplum is open source, so everybody can download the code. It's on GitHub. Everybody can compile it. We have Ubuntu builds that you can just run apt-get install, so you don't even need to compile it. The current statistics, there's about 2,500 people who started the project, 780 project forks, there's 170 contributors. So I think it really is the most actively developed MPP version of Postgres in the world, where we're taking lots of Postgreses together to solve one analytical problem. So if you're interested in this area, definitely check out the GitHub. And as well, you can join the mailing list. There's about 300 users on the mailing list. There's a Slack channel and a really great YouTube channel as well, where there's over 100 videos about this technology. So with that, I highly encourage you guys all to get involved with it and to help Postgres be really to grow from where we are now, which is one of the most popular databases in the world, to as the title of this talk was saying, is to a scalable and evolving analytical platform where we can solve and tackle some of the hardest problems in the world using the power of many Postgreses together. So with that, I'll open up for any questions. Yep.
So do you have any question?
Actually, I have a few. First of all, is there any limit on the lower side? I mean, what is the logical minimum number of Postgres to instances, Greenplum instances?
Yeah. So you need to have a minimum of 2. One would be, so there's a master Postgres which takes the connections and at least one worker. So at the minimum you'll need 2, but they could run on the same server. You could run, the minimum number of servers is 1, but the minimum number of Postgres is 2. 1 for the master and 1 for the worker.
Okay, thank you.
And you can run it on VM, Docker, laptop, cloud, anything, especially just for testing. It just depends on how much hardware you have, how much performance you can do.
Okay, thank you. The other question is, what about any time frame? I mean, you said it is based with 9.1.
Yep.
So basically, if I'm using 9.6 or 10, my schemas and there are functions
Certain things,
that I can't just take into Greenplum. So
Yeah. We're targeting 9.4 by within about 6 to 8 months. And then thereafter we'll continue. So the next milestone for us really is to reach 9.4. In fact, we were on, about a year ago, we were based on 8.3. So in the last 6 to 9 months, we've changed 8.3, 8.4, I think 8.5 if that exists, 9.0, 9.1. So we're getting quite good at it. And the other part is, we worked on Greenplum for about 10 years without changing the version of Postgres. So we started on 8.2, and in the last few years we've been really making sure that the differential code between Postgres and Greenplum, for example, the stuff that interconnects between them can be cleanly separated. And we're moving really eventually towards essentially extension model, where you take the normal Postgres and then just apply extensions. But because we have so many users, we're not just stopping and starting over at the latest version, but doing it incrementally. And so basically, as far as your question of timeline, it'll be, by next year, we'll be probably on 9.4, and then quickly thereafter, we'll start being in sync with the latest version.
You actually answered my next question. Is there any plans or chances to get Greenplum back to Postgres core?
Yeah, there's absolutely no technical reason to be on a different version. It was just that there was so much work to be done, and we were, a smaller team, that the priority was to make the interconnects and the parallel processing work. And then we said, oh, okay, now, whoops, we're a little bit behind. Let's catch up. But there's absolutely no technical barrier to using any version of Postgres. So we'll certainly do that.
Okay. Hi, just a quick question. You mentioned Linux kernel extension to couple per user Linux CPU usage.
Yep.
Okay, but isn't that used in mainstream Linux? Just I don't know.
Sure. So no, yeah, we're using mainstream Linux. So we're just calling the C APIs. So essentially, what we do is we created these extra catalog tables where you can map usernames to a group. And then when you start running the queries, we ensure that the Postgres processes that run the query are running in that Linux C group. So C group is the technology. So when that process kicks off, it needs to run inside a C group. And once it's in a C group, then Linux will ensure, based on the settings of that C group, how much CPU and memory you can take. So we're not reinventing that wheel, we're just connecting that the queries can be mapped to a specific C group without would still be in the same database. You don't need to have like a mirror and say, okay, you're going to run this workload in this Postgres and then have a replica. No, it's all just one database, but the queries themselves at the query level can get mapped. The Postgres processes get mapped to the right C group.
Okay, thank you.
Yeah.
No other question?
It's not a question, it's a comment. I have some information about Greenplum. Whenever you want to leave the room, you can ask me, we'll set a table with Greenplum information. Any other questions?
No more questions? Okay, thank you very much for the talk.